We've talked about chemical reactions. Chemical reactions involve chemical changes. One substance is destroyed and is changed into one or more new substances. But in these changes, the individual atoms remain unchanged. They're just getting rearranged, put back together with each other differently. So a combustion reaction is one type of chemical reaction. And here we have a substance combining with oxygen. And it's going to form one or more oxygen-containing compounds. It's also going to give off heat. And so the heat that's given off by the combustion reactions is what it makes it useful for supplying energy. So chemical equations are just a shorthand way of describing chemical reactions. And in the most basic form, we have the reactants on the left and an arrow pointing to what happens, the products that are formed. So reactants on the left, those are the things that react. The products are on the right, those are the things that are produced, right? Kind of makes sense. There's a lot of information about the reaction that can be given in this equation. The formulas of the reactants and products and their states. So by state, we mean physical state. We've got gas, liquid, solid, and aqueous. Aqueous meaning it's dissolved in water. And so those are the four state symbols that we will see. Equation is also going to give us relative numbers of reactant and product molecules, and it can be used to make predictions like, well, if I had 1 kilogram of this reactant and this reaction occurs, what mass of product would I get? So let's first look at the combustion of methane. Methane is CH4. It combines with oxygen to produce carbon dioxide and water. If we look at this, and we remember that these letters represent individual atoms, that's 1 carbon atom, 4 hydrogen atoms, this is 2 oxygen atoms. We see that we're starting out with a total of 2 oxygen atoms, but over here in the products, there's 2 oxygen atoms here and 1 over there. And so it appears that we've created an oxygen atom. Is that possible? No, that's not going to happen. So something's not quite right. We also have an issue with the hydrogens. There's 4 hydrogens on the left and only 2 on the right. Well, maybe those 2 hydrogens that disappeared got transferred or transformed into an oxygen. No. So this equation is violating the law of conservation of mass, which, like the law of gravity, we can't just decide not to obey. So the problem is with our equation, not with science or nature. So we need to fix this equation. We call that balancing the equation. You can think of like a teeter-totter or a balance board where you want it to be flat and balanced, and so you need to have equal masses on both sides, right? So here we've got space-filling models illustrating these different molecules. Here's our methane molecule. And when we balance this, we're going to put a 2 here and a 2 over there, which tells us there are 2 oxygen molecules. We still have 1 carbon dioxide and 2 water molecules. And I really like how they illustrated this because, you can just imagine these being like little Lego bricks that you can pull apart, right? Round Legos. Why hasn't anyone thought of that? So there are 4 white ones over here, and you can pull those off, and that's those 4 white ones over here. And there's a total of 4 red ones. Well, we've got 2 of the red ones here with the 1 black one, and the other 2 are over there. So we took all of the atoms that were present initially, and we're using all of them at the end. Does that make sense? That's all we're doing when we're talking about balancing an equation. the letters represent these little balls, these little building blocks. So here's a chemical equation, and we are asked how many oxygen atoms are on the right-hand side of this equation. So the right-hand side is over here. There are two things, right? There's this Fe2O3 and there's also CO2. So in this guy, how many oxygen atoms are there? A total of 6. There are 2 of those, and each of them has 3 oxygens, right? The 2 in front of that just means I have 2 of those. It's nothing crazy or special. And then over here, how many oxygens? 8. So I have 4 times 2, which is 8. And so the total is 14. Everybody okay with that? If we can't do this, we can't balance equations. How many are on the left side? 14. Because over here we have 4 times 3, which is 12, and 2, and that adds up to 14. So this is a guide to balancing chemical equations. You do not have to follow these steps like you really should follow the steps for finding the empirical formula. That's like do this, do this. This is more of a guide. Start with the skeletal equation. So that would be the correct formulas for all your reactants and products. Get them on the right side, get the arrows and the plus signs in there. Then you start balancing the atoms. As we work through examples, we'll see that oftentimes you can just start with the first element and it'll work out just fine. But if things get a little messier, what we're wanting to do is we're wanting to balance atoms that are in the more complex substances first, before anything that's a pure element. And we're going to balance atoms that occur as free elements last. Sometimes you can end up with coefficients that are fractions, and so we need to clear those out. To have a balanced chemical equation, it should have the lowest whole number coefficients. And then you should always check to see that you did it correctly. So these examples are going to give us a little practice in nomenclature as well as balancing chemical equations. So here, the description of the chemical reaction is in words. So write a balanced chemical equation for the reaction between solid silicon dioxide and, that's our plus, solid carbon to produce solid silicon carbide and carbon monoxide gas. So mostly what we're doing here is we're just writing the formulas for these compounds to make our skeleton, and then we can balance it. What kind of a compound is silicon dioxide? You've got acids, ionic, or molecular. It's molecular because silicon, the first element, is on the right side of the line. Just barely, but it is. So to write silicon dioxide, what's the formula going to be? Si for silicon, O2, dioxide. And they tell us what the state is because they don't expect you to know that. So solid. And a plus sign. I'm going to leave a little space because I might need a coefficient there. Solid carbon. What's the formula for carbon? C. C. Si. C. It is C. Yes. So here we have an element, and writing chemical equations is probably one of the biggest places where you have to remember diatomic elements, right? Horses need oats for clear brown eyes, those 7. And So carbon's not one of those. If we have oxygen, oxygen is a diatomic element, so when we write the formula, we have to write O2. And yes, it matters. Okay, arrow, solid silicon carbide. Well, that one doesn't quite follow the rules for molecular compounds, but we can figure it out. So that must be silicon and what other element? Carbon. And there's no numerical prefix for the silicon, so there must just be one. There's also no numerical prefix for the carbon, and according to our rules that we learned, it should be silicon monocarbide. But in the absence of any other prefixes, we can assume that it is one carbon. I used to have fun with Siri because I'd ask her, hey Siri, what's the formula for silicon carbide? And she'd say, the formula for silicon carbide is sick. It's just always cracked me up. She doesn't do that anymore. Anyway, this is sick, right? Silicon carbide. And it's a solid. And you have to find your amusement where you can. Carbon monoxide, right? Another molecular compound. The first element is carbon. And how many oxygens? One. And it says this is a gas. So that's our skeleton. Usually the best method is what's called balancing by inspection, which means we're going to look at the elements one at a time and get them lined up. So let's just start with the first one. So here's silicon, and we also have to, make sure that we're looking at all of the compounds on the left side. So there's one silicon over here, and how many silicon atoms in the products? One. So that's already balanced. How many oxygens are on the reactant side? Two. And how many on the product side? One. We can't change formulas. We can't take away the two. We can't add a two here because that's changing the compounds, and then you're talking about a completely different reaction. All we can do is put coefficients in front. So what we need is two carbon monoxides so that we have two oxygen atoms. And the last element is carbon. I have one carbon here, and how many carbons on this side? Three. There's these two, and then there's also one over here. Some elements you'll find in multiple compounds, and you have to consider all of them. So we need 3 carbons, and so we can put a 3 here. Balancing the element last is nice because whatever coefficient I put in here, it doesn't mess up anything else that I've already done. Right? If I leave oxygen or silicon for last, I could end up messing up something else. Any questions? Here's another one. Write a balanced equation for the combustion of ethane, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. It's a lot of gas. So we have gaseous ethane with gaseous oxygen to form gaseous carbon dioxide and gaseous water. Well, they gave us the formula for ethane. So that'll be our first one, C2H6. There's a gas. And combines with gaseous oxygen. So oxygen is the other reactant. What's the formula for elemental oxygen? It's O2, because oxygen is one of the diatomic elements. So it's O2, and that's a gas. We have an arrow. And then carbon dioxide would have what formula? CO2. carbon, 1 carbon, dioxide, 2 oxygens. And water. What's the formula for water? H2O. And we're told that this is a gas. The reason that the water formed as a gas is because a combustion reaction gives off a lot of heat, and this is going to be hot. So as the water is formed, it'll be in the gas state, and then when it cools off later, it'll condense into a liquid. So I'm going to show you another method of balancing that can be helpful. If you don't like it, you can just use the other method. This is sort of a tally method where I'm going to take inventory of what I've got. So I'm just going to list the elements. I have carbon, I have hydrogen, I have oxygen. And then I'm going to look at each of the compounds or elements and identify how many atoms I have. So in C2H6, I have 2 carbon atoms. How many carbon atoms in O2? None. Instead of writing a 0, which looks like an O, we're just going to dash. And then over here, CO2, there's 1 carbon and no carbons in water. And then for hydrogen, this one has 6, and O2 has none. CO2 has no hydrogen. Water has 2 hydrogens. C2H6, there's no oxygens there, but O2 has 2 oxygens. CO2 has 2 oxygens, and water has 1 oxygen. So I'm going to balance the first element first. The total on the left side is 2, right? The total on the right side is 1. So, excuse me, what can I do to make that 2 carbons? Put a coefficient, right? And that's going to multiply everything underneath. So now I've got 2 carbons, and I have 4 oxygens. So changing that one changed the oxygen, but we weren't looking at the oxygen yet, so it's okay. The next one's hydrogen. On the reactant side, how many hydrogens do I have? 6. And over here I have 2. So how do I make 2 into 6? Multiply by 3. So multiply by 3, and that's also going to multiply that's not right. Multiply by 3 and I get 6 is what I meant to do. And multiply 1 by 3 and I get 3. So the carbons are balanced, the hydrogens are balanced. Now for the oxygens, I have 2 on the reactant side and 4 plus 3, which equals 7 on the product side. The oxygens here come in pairs. You can't get an odd number of oxygen atoms. So you could use a fraction. Most of my students don't like fractions that much. If you put 7 halves in here, 7 halves times 2 is 7, right? But then you have a fraction and you need to multiply everything by 2. I call this the odd-even problem. I need an odd number of atoms over here, and they're coming in even numbers over there. What happens to an odd number when you multiply it by 2? It becomes an even number. So if I multiply all the coefficients by 2, then I won't have any odd numbers anymore. So I'm going to multiply this by 2, which would make this 4, make that 12. This is the one I'm working on. I haven't written anything there, so I'm just going to leave that alone. I'm going to multiply this by 2, and we'll multiply this by 2. And now I have 8 plus 6, which is 14 oxygens. So if I need 14 oxygens and they come in pairs, how many pairs of oxygens do I need? 7. I didn't change the balance of carbon and hydrogen. Now that's probably pretty tedious to do all the time, but I hope it illustrates the thought process that goes on. Any questions? Let's do one with ionic compounds. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. So we've got 2 reactants and 2 products. So these are ionic compounds. How do we write formulas for ionic compounds? We start with the ion formulas, right? So each ionic compound in Chem 1A has 2 ions, 1 cation, 1 anion. Here the cation is lead-2. So the symbol for lead is Pb, and what does the Roman numeral 2 tell us? It has a charge of 2+. The Roman numeral is the charge. Nitrate is NO3 minus. Why? Because it is. You just memorize it. They decided. So if I want to make a compound from these, I need to look at their charges and figure out how many of each do I need, right? So I need 2 nitrates to balance the charge on the lead. So that's going to be Pb NO3 2, and I'm told that's aqueous. This is a polyatomic ion. It has more than one kind of element in it. I need to put the parentheses or the shrink wrap around the outside so I can say how many outside the shrink wrap. Okay. Our other one is potassium chloride. What's the symbol for potassium ion? Potassium ion is K, and what's the charge? +1. Chloride comes from chlorine, and the charge is -1. So these charges are the same but opposite in charge, so we need 1 of each. That's aqueous. What's happening here is that we're just rearranging the ions. So here potassium was with nitrate. Over here, sorry, that's not potassium. Here lead was with nitrate, and now over here lead's going to be with chloride. So I'm going to move my symbols over, partly because I can. So lead-2 chloride. What's the formula for the compound? PbCl2. This is just a single element, doesn't need any parentheses. So we want to conserve the environment, we want to preserve the environment. We don't want to use shrink wrap unless we need it, right? More plastic in the dump, not good. This is a solid, so we write S. And then over here, we've got potassium with nitrate. This happens a lot with these oxyanions. In a chemical reaction, they don't come apart. They just come off as an ion, and they go and they get together with a different ion. So we can balance NO3 as a unit. If you don't feel comfortable with that, you can balance the nitrogens and oxygens separately. It just gets a little messier. So +1, -1, that's just going to be KNO3, and they tell us it's aqueous. Any questions? Now we can balance it. So On an exam, I'm not going to give you a question like this and ask you to write a balanced chemical equation. I'm going to give you names and ask you to write formulas. I'll give you formulas, ask you to write names. I'll give you a skeleton and ask you to balance it. Well, let's just start with the first element. Lead, I've got 1, and over here I've got 1. So that's all good. How many nitrate ions? 2, right? 2 right there. How many nitrate ions over here?
1.
Just 1. So I need more. So I need 2 of those guys. So I get 2 nitrate ions. Here I have 1 potassium ion, and I go look over here, and now I've got 2 potassium ions. So I need to put a 2 in front of KCl. How many chlorines? 2. And how many chlorines? 2. They took care of themselves. That happens a lot with ionic compound chemical equations. Any questions?